Okay, I thought I'd make a little summary of just what we've done. And I've been trying to give a number of examples. So I've talked about Pelly state transfer. I've talked about uniform mixing. And we'll be talking more about that today. Now, we have examples of Pelly state transfer with, well, K2 and P3. And then we saw examples of Cartesian powers, which means we have infinitely many examples of Pelly state transfer. And we do get uniform mixing on the D cubes, so we get all that. So today I'm going to talk about uniform. I've also talked about well, walks on bipolar graphs, but we're going on that, so I won't put that down here. The other point we're seeing is if we have PST from A to B at time t, then we get PST from B to A. And that implies, well, that tells us that PST implies periodicity. Now, one of the things I want to prove fairly soon is that if there's only finite, if you look at connected graphs with maximum valency K, so nobody's got valency greater than K, then there's only finitely many such graphs that contain periodic vertices, and so there's only finitely many such graphs that contain PST, and so that tells us that PST is rare. And that proof depends on periodicity. Okay, so that's the situation at this point. So we haven't built up a lot of theory yet. We basically know if you have PST, you have periodicity, and we know that Cartesian powers will preserve either periodicity or Pelly state transfer if the times match up. So are there any questions at this point? Okay, so I want to talk about walks, continuous walks on bipolar graphs and the connection to Hadamard matrices. Now, well, best thing, so in the last lecture we worked out some information about the structure of the transition matrix for bipolar walks, and we'll be using that, but I should start by talking about Hadamard matrices. So the terminology is a bit confused. By mathematical standards, not too bad. So a complex Hadamard matrix is a flat complex invariant matrix such that H star at H is equal to n times I. So it's a unitary, well, up to scaling. So 1 on root n H is the unitary matrix, and flat means that all entries have the same absolute value. Now, for me, when I say Hadamard matrix, it's going to be a flat real matrix such that H transpose n equals n transpose I. And so a flat real matrix, again, this question will have, can be scaled so the entries are all equal to plus or minus 1. So these are the standard examples. I think I don't have them drawn there, so I'll do one now. So to give one trivial example, that's a 2 by 2 Hadamard matrix. Okay, and as I said, the complex Hadamard matrices correspond to flat unitary matrices modulo scaling. Okay, now Hadamard matrices play an important role in design theory and in coding theory and in various other places. They're very interesting structures. I wanted to give, actually, I did have the example here. So the examples I want to give for a complex Hadamard matrix, take theta to be an nth root of unity, not the identity, then the Van der Waals matrix is a complex Hadamard matrix. The next thing is if H1, H2 are complex Hadamard matrices, so is the Schur product. Oops. And the point about that is so is the Schur product. And so the Schur product of complex Hadamard matrices is a complex Hadamard matrix. Chronicle product of complex Hadamard matrix is a complex Hadamard matrix, and the chronicle product of real Hadamard matrices is a real Hadamard matrix. So, so once we have one, we get equally many. And here I've drawn, for education, there's the 2 by 2 Hadamard matrix. It's the only one, and there's a after, well, I'll talk talk about in a second, this is a 4x4 Hadamard matrix. So the rows are orthogonal, the columns are orthogonal, and the entries can be complex. Now, I want to define equivalence of Hadamard matrices. Now, it's fairly clear that if I have a complex other matrix and I multiply a row by a complex number of norm 1, it's still going to be a Hadamard matrix. So that's a scaling operation. You can compute rows, you can compute columns, and so anything, if you have a Hadamard matrix H and you commute rows and columns and scale rows and columns, you get a second Hadamard matrix. Those two matrices are said to be equivalent. Okay, so that's the definition. Simply, if I can get from one to the other by scaling by complex numbers norm 1 and by permuting rows and columns, then they're equivalent. Now, it's obviously true that if H is a Hadamard matrix, so is its conjugate transpose. But the convention is that they're not equivalent. And so, in fact, I mean, sometimes there will be, but often they will not be equivalent, so that you can't necessarily transform a Hadamard matrix into its transpose. And so the convention, as I said, is that they're not equivalent. I mean, this is largely a convention, so that they're equivalent just says row and column operations. Now, permuting rows and permuting columns, well, to get a permute rows, you pre-multiply by a permutation matrix. And to scale, you pre-multiply by a diagonal matrix with entries complex numbers norm 1. Now, the product of a permutation matrix and a diagonal matrix is usually referred to as a monomial matrix. Okay, so you've got it's a weighted permutation matrix. Okay, now the usual convention would be that the entries the weights are all non-zero. Okay, so a unitary monomial matrix. So a monomial matrix is an n-rated matrix where each entry has exactly one, each row has exactly one non-zero entry, and each column has exactly one non-zero entry. And any such monomial matrix is the product of a diagonal matrix with non-zero diagonal entries with a permutation matrix, so it's invertible. So in fact, the monomial matrices form a group, but you can forget that. Now we're dealing with our scalings are all given by complex numbers of norm 1. Now a diagonal matrix whose entries are complex numbers of norm 1 is a unitary matrix. Okay, and so I can talk about a unitary monomial matrix. So it's a matrix where each row has exactly one entry of norm 1, and each column has exactly one entry of norm 1. And so using monomial matrices, so I can then say something along the lines that two Hadamard matrices are equivalent if there's a monomial matrices M1 and M2, such as M1, H1, M2 is equal to H prime or H whatever. So that's a lot of fuss about it. What's actually fairly simple. But unfortunately, you talk about the word equivalent gets thrown around a lot, so it's best to be explicit. Now, the first thing about Hadamard matrices is that if a Hadamard matrix of order n by n exists, then either n equals 2, and you saw it above, or 4 divides n. Now, it's easy to see. So a Hadamard matrix in that current usage just means it's a real matrix. And so if you have a Hadamard matrix, we can always scale the columns so the first entry in each row is equal to 1. Okay, so the first row is all 1 vector. Now the second row is going to have entries 1 and -1, but it has to be orthogonal to the first row. The rows of a Hadamard matrix are pairwise orthogonal. Now the only way you can, a 1 minus 1 vector can be, well, if you have a 1 minus 1 vector orthogonal to a 1 vector, then that second vector must have equal number of 1s and -1s, so that tells you that it must be even. Okay, now it's an exercise. It's an easy exercise. I'm not going to sign it. So the idea is, so now that means you can assume that you had a matrix that the first row is all 1s, and there's an even number of 1s, say 2m. The second row can be taken to consist of m1s followed by m -1s. Now, if you think about the third row, you'll get this condition. Okay. But I'm not, and so you can look up Wikipedia. It's easy. We don't. It's not going to matter too much for us. But the point is that now this is quite interesting. The open question, and this is probably the longest standing and most important open question in algebraic combinatorics, is it true that if 4 divides n, there is an n by n Hadamard matrix? I think the first open case is still less than 1,000. I didn't bother checking. You could check now. So the converse to this is an important open question. There are constructions, people keep pushing the boundaries, but it doesn't move very fast. And as I said, the smallest value of n, which is divisible by 4, and we don't know whether there's a Hadamard matrix or not, is below 1,000. Okay. Now, as I said, Hadamard matrices are interesting for a number of reasons, and the complex Hadamard matrices are of interest largely because of things that physicists want to do, which I probably won't get to in these lectures. So the physicists are interested in complex Hadamard matrices, and we'll see some more. We'll probably see some more examples later on. The theorem, the connection to what we're quantum walks, or one of the connections given by this theorem. We have a bipolar graph and n vertices. Actually, I don't know. I don't mean show. That's the thing. So the point is that X admits uniform mixing if only if either n is 2 or 4 divides n, and if X is regular, then n is the sum of 2 integer squares. I'm pretty sure I got the proof's coming. Yep. So now the way the proof's going to work is we're going to construct a Hadamard matrix when there's uniform mixing. Okay, and so then we just apply the results of Hadamard matrices. Now, when you're dealing with these sorts of situations, things break up into 3. You either have n as a square, or n to the sum of 2 squares, or 4 divides n. And so this is sort of one of these 3 alternatives. Anyway, so I'm not giving the full proof. I'm just going to construct the Hadamard matrix and let you think about the rest. So if X is bipartite, from the stuff we're doing in the last lecture, we can assume that we can assume that U of t has got this form. So you've got block diagonal, C1 and C2 are real, and S is real. Okay. Now, U of t is complex. Okay, I'm not making any assumptions I'm not reducing a real case. We just take our transition matrix for our bipartite graph, then we can assume that U of t has got this form. Now, if there's uniform mixing at time t, then this matrix must be flat. And so up to a scale, you can assume that implies that all real entries must all be plus or minus 1 over root n, and the off-diagonal entries must all be plus or minus I over root n. So your matrix, if you scale it properly, you now have a matrix with entries plus or minus 1 and plus or minus I, and it's unitary, or 1 over root n times that is unitary. So that's already special. But it turns out we can go a little bit further. This is a little confusing. I'm computing. I'm taking this times this inverse, and this is just the way I work it out on paper. So when I multiply this by this, I get that. Now I multiply this on the right by this. Now this is the inverse. This is the inverse of that. So if you like, there's something missing in there, and I can do it. There's a matrix missing in there. And so now this is a unitary matrix. Okay. And so what we're getting is that this matrix here is similar to this matrix. Now this matrix is real, and the entries are plus or minus 1 on root n. So it's a Hadamard matrix. Okay, and so that gives you the fact that 2 divides n, that n is even, and if n's not 2, it's divisible by 4. The second part about the sum of 2 squares is hidden in one of the exercises. The point well, the point of this example is if we get uniform mixing on a bipolar graph like the D cube, then we're constructing a Hadamard matrix. In fact, the Hadamard matrix for the D cube is going to be the Kronecker power of the matrix minus 1, 1, 1, minus 1, 1, so the 2 by 2 matrix. Okay, so and so this is it's an unexpected connection between combinatorics and quantum walks. Any questions at this point? Okay, so now I want to go and talk about periodicity. So we've seen that if you get perfect state transfer from A to B at some time tau, then you get perfect state transfer from B to A at time tau, and in particular, A and B are periodic vertices at time 2 tau. Now, later on, I'll talk a bit about discrete quantum walks, and you do not get periodicity in that case. The reason you get periodicity is because the Hamiltonian, the x by h, that h is symmetric, and because of that, we get the periodicity. Now, in more general situations where h is not symmetric, periodicity goes away, which is a pity because periodicity is an important tool. And so you don't prove that most graphs don't have perfect state transfer, you prove most of them don't have periodic vertices. Let's go through the periodicity a little more carefully. So I'm going to assume I've got real density matrices D1 and D2, and that there's transfer between them. At time tau, this is true. Now, so because the states are real, you take complex conjugates, you get this. Now, the point about this calculation is that all we're using is the fact, we're using the fact that the Hamiltonian is real and symmetric, and we're using the fact that these densities are real. Now, I think I went through a version of this argument before when I was dealing with vertex states, but my point is you don't need much. The important thing is that these are real. Okay, in that case, if you get perfect state transfer, actually, I've probably got a proof coming up now. Think about it. No, you got to work at it. So, and so if we get transfer from one real density to another, then we can call this perfect state transfer. And the other point is that the two states are periodic time 2 tau. It's worth noting that this second condition holds if and only if U2 tau commutes with D1 and D2. And so it commutes with any linear combination of products of D1 and D2. Now, it's hard to overemphasize the importance of when things commute in linear algebra. That's an implied truth at this point since we don't need it. But so this is a fairly strong condition on U of 2 tau. Okay. Because if it commutes with these two matrices, it commutes, as I said, with anything in the algebra they generate, and that's a lot of matrices to commute with. Okay, so the periodicity is a property of real states and real Hamiltonians. Okay. And so that's the background. And this is what I'm saying. And it follows that periodicity is a necessary condition for perfect state transfer. And so it's periodicity that we'll work with. Turns out to characterize perfect state transfer, we need linear algebra conditions, which basically includes the periodicity. And we also need number theoretic conditions. And then there's some parity conditions to fuss with. So we can characterize when perfect state transfer occurs. And there's a polynomial time algorithm for determining whether a graph admits perfect state transfer. Okay, but as I said, the conditions involve both linear algebra and number theory, which is one of the reasons this stuff is interesting. Now, another comment here. Now I'm just reducing to the case where I'm dealing with pure states. So these could be vertex states, EA transpose, and the BE transpose, but pure states is what I need. Now, the point here is, in that case, my density matrices are projections. They're not just positive semi-definite, they're projections. Their argument is a 0 and 1. They're special. Now, the important thing here, and this is a fact in linear algebra, is that if a matrix commutes with a projection, it must fix the image of that projection. Now, I've written out a proof for the case that we care about. If M commutes with WW star, then I can get that multiply this on the left by W, then W star W is 1, so I get MW is equal to this. And now, and where's my, this is just a scalar. What have I done? Heaven help me. Oh, yeah, I've got the, yeah, there it is, M, and so I can push the M, bring the M into here by the commuting condition. And so now I've got that M applied to W is W times this, but this is just a scalar. Okay, and so that tells you that W is an eigenvector. So if you commute with the projection, rank one projection, then the columns of that rank one projection are eigenvectors for your matrix. And so in this case, you get that if you get, so in this case, if we have PSD, well, actually, all we need is, or periodicity, we get this commuting condition. And then we learn that at time tau, the vectors y and z are eigenvectors. Okay, so that's surprising. But the other thing is, it's actually quite important to realize that it's surprising how often you can get to use it. If you commute with a projection, you fix the Connell space. Okay, we'll save that for now. Okay, so that's what I want to say about periodicity for now. The problem is, I said I can use that to rule out, I can rule out periodicity under a wide range of conditions. And so we've got to start working on that. And this involves something called the ratio condition and also another concept called eigenvalue support. So we're starting to build up some of the theory now. Okay, so we're just considering about a continuous quantum walk, and I'm still at this point just working with transfer between arbitrary states. At some point, I'll drop down and make stronger assumptions, but for the moment, I'm not worried about that. So well, maybe I can should do something like this. So let's think about the case where we're thinking about PSD with a pure state. So actually, I can even take E UT EA. Now, okay, so if I have this is the outer product of this vector with itself. Okay, that should be now the point is that everything at any time, what you're looking at is a vector of you're working with the outer product of a vector of the form UT EA. And so that means all the vectors that you see can be written as the form U to T EA. So that's the vector space you're working in. Now, the thing to bear in mind is that U of T is a polynomial in A. So everything you see is in this space. Now, you can actually go a step further in terms of the spectral decomposition and say we're dealing with this. These two spaces are the same because the idempotents are a basis. They're an orthogonal basis. So the issue is that we think ourselves as working in C to the D, but we're really working in some subspace of C to the D. And in fact, it will be a proper subspace of C to the D in most cases. Now, this is related to the fact that when if I'm doing my computations, well, I have U of T, EA, T, U to the minus T equals sigma E to the IT, C to S. Yeah. Now, I'm writing this as a sum over all R and S, but I don't really, I don't care about the terms where this is 0. Now, this vector here is the, well, this is a column vector, this is the row vector, and the only way this can be 0 is either this is 0 or this is 0. Okay, so we don't really, so what this is telling us is I don't care about the eigenvalues theta r such that ER times E0 is 0. Now, ER times E0 is the ER times EA is the projection of EA onto the eigenspace. And so we don't care about the eigenvalues where the projection onto the eigenspace is a 0 vector. So that tells us that there's, we don't need all the eigenvalues. And a lot of the time we can sort of more or less ignore this fact, but it's true. And in fact, in general, we'll find it's unusual to find that we need all the eigenvalues. The sort of problems we'll be looking at. So the point of this then is that the action we're looking at is not on the full complex space, it's on a subspace of that vector space. Okay. Now in the notes we'll refer to this as walk modules, so I may not be going to that in these lectures, but so on that subspace. Now I will make a comment that in people dealing with the spectral theory for infinite-dimensional operators work with exactly these subspaces. Okay, so these are important in various ways, but for us, it's just that if you're not in that subspace, then we don't care about you. We're not going to see you. I'll say a bit more about that as I go on. So so now this is going to, from my point of view, justify some terminology. So I want to I'm going to look at the pairs of eigenvalues theta k and theta l such that ek d el is not 0. And I'm going to call that the eigenvalue supported D. Now, it's a little funny because it's a set of pairs and you'd rather have a set of eigenvalues. It turns out in the cases, first few cases we look at, there will be a set of eigenvalues, but we don't need to worry about that. So the definition of the eigenvalue support is simply it's the pairs theta k, theta l such that this is not 0. Now the other point, and I have it here. I'm not sure where this came from. Now, I think I've got something unjustified here. Okay, where did I write the transfer stuff? Excuse me. Well, let's do it from here. If I, so I'm looking back at it. This is our transfer condition. If I multiply on the left by e to the k, and on the right by e to the l, then, well, e to the k, its column space consists of eigenvectors for u of t, and the eigenvalue is just e to the i theta rt. So if I multiply on both sides by, what we get is that ek d1 dl equals e to the it theta k. The it theta k ek. Now, this is a complex number normal 1. So one thing this tells us is that D1 and D2 have the same eigenvalue support. Okay, and so that's a necessary condition for state transfer, and it's reasonably powerful. Okay, but the point I want to focus on now is this guy. So let's consider about the quantum walks we're dealing with. The Hamiltonian is real, and the states are real. Now, if the Hamiltonian is real, then the idempotents are real because they're polynomials in Hamiltonian. And the states are real by assumption, and so this is real, 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 this is real. So this has to be real. It's a complex number of norm 1. And so your only choices are that this is 1 or minus 1. Now, okay, so you've got 2 choices. You can make your life a little bit easier by saying, well, let's look at what happens at twice if I look at replace t by 2t, then this is just a square of this, and that's the square of minus 1 is 1. So we know this is 1 or minus 1, and we can always put ourselves in a position where that's equal to 1. So now I go back to where it was before. Sorry about this. Now, and so if we're in a position where some sigma, which is likely to be the twice the PST time, we have e to the I sigma c to k minus c to L is equal to 1, then, well, then the exponent here must be a multiple, integer multiple of 2 pi. So I'm going to write it as 2 mk comma L pi for some integer mkl. Okay, so, and now, I'm sure I should write something in. So we have theta. So then the conclusion is that if these 2 guys are both in the eigenvalue support and these 2 things are distinct, theta k and theta L, then this ratio is a rational number. Okay, now that won't seem too impressive at this point. First thing to bear in mind is the eigenvalues of graphs in general a long way from being rational numbers. I'll say a lot more about this before too long, but so being rational, the eigenvalues of, well, if an eigenvalue graph is rational, it must be an integer. I'll be explaining this later on too. So if an eigenvalue graph is rational, it must be an integer. And graphs tend not to have lots of integer eigenvalues. It's easy enough to produce counterexamples of that, but this still statement is still true. So this is a strong restriction on the eigenvalue support. So what's happened is I've introduced this concept of eigenvalue support, and then I said that if we're periodic at a vertex, then we're getting this condition on the eigenvalue support. Now, it's a bit hard to use at the moment because we don't know much about the eigenvalue support, but we do know it consists of eigenvalues of the graph. And so as I said, this is strong. Actually, I should put in the, let me just, we have, going back here, we have I sigma theta k minus theta L equals 2 m1 I and I sigma theta. So we have these 2 conditions, and if we just take the ratio, divide the second equation by the first, we get the claim. Okay, so as a consequence of periodicity, we get this condition on the eigenvalues. So this is a constraint. It's a number theoretic constraint on the eigenvalue support. The eigenvalue support is a numeric linear algebra concept. It's a subspace, nice subspace, and whereas this is a number theory condition. So we're going to have to do some number theory before we finish. So this is a necessary condition for periodicity and therefore a necessary condition for PST. So let's put this to an example. So we proved that P2 had perfect state transfer and that P3 had perfect state transfer. And so, by engineering induction, there should be perfect state transfer for Pn for all n, but unfortunately that doesn't quite work. We're going to prove you don't get PST between the n vertices, the vertices degree 1 in P4. So I've written down here the characteristic polynomial of P4 is 2 to the 4th minus 3t squared plus 1. I gave you the one-sum formula, so you can work it out from that, or you could dig it up, get Sage to compute it, or you could trust me. There's 3 choices. Now, this is equal to t. Well, you can write this in this form, and then factor it. So although it's a quartic, it factors into 2 quadratics. And so we'd find that the eigenvalues are 1 plus or minus root 5 on 2 and minus 1 plus or minus root 5 on 2. So we know the eigenvalues of P4. And that's all I'm going to need. Now, I've written them down in increasing order, and there's a reasonable chance I got this right. So I've gone from theta 3 to theta 0. This is the largest eigenvalue. It's positive. This is positive, negative, negative. So 2 positive and 2 negative. Of course, this is minus this, and this is minus this. And we knew that already because you know that the spectrum of what about a Pilot graph is symmetric about the origin. Okay. Now, okay, so we've got the eigenvalues. So we want to get the next step is obviously we get the eigenvectors and the projections and grind away. We can save our life, save ourselves some work here though. The point to bear in mind is when we look at an eigenvector for the path on n vertices, in this case the path on 4 vertices, I showed before that if we had an eigenvector which is 0 on this vertex, then that implied turtles. That implied all the other entries are 0. So the point about the path is that the eigenvalue on path for 4 vertices, eigenvalues are simple, and that each eigenvalue has a non-zero entry on the first vertex and isommetry on the last vertex. So in particular, that means since we can scale eigenvectors for free, I can assume my eigenvector has got first entry equal to 1. But the important thing is it's not 0. Okay. And so it follows that no eigenvector for P4 can be 0 on the first or last vertex. And so in particular, we get this. So the point is that ER applied to E1 is an eigenvector. Okay. And so this is an outer product of an eigenvector with itself. Okay. And so, and we know that the first entry of this eigenvector is not 0. And so we know that this entry of this matrix is not 0. And so the eigenvalue support of the vertex consists of all pairs theta I, theta j. So without actually computing an eigenvalue, I've worked out that the eigenvalue support consists of all possible pairs. Now, and so in that, but now you just look at the, theta 1 minus theta 2. Yeah, theta 1 minus root 2. I got that wrong, I think, but I'm probably getting my 1s and 2s. There probably should be 0s. So, yeah, that's excuse me. So theta 0 minus theta 2 is 2 root 5. And theta 2 minus theta 3 is 1. And so the ratio is root 5. That's not rational. So that's a proof that the path on 4 vertices doesn't have perfect state transfer between the vertices of degree 1. Now, I might make this an assignment question. You can prove that the path on P4 vertices, if you had perfect state transfer between vertices 1 and 4, you would also get perfect state transfer between vertices 2 and 3. That's just a linear algebra argument. Okay, so there's no perfect state transfer on the path on 4 vertices. Although you might say, well, what could there be perfect state transfer from, say, vertex degree 1 to a vertex degree 2? Now we'll see before too long that's not possible. Okay, so there's no PST on the path on 4 vertices. You can also get the eigenvalues, the characteristic polynomial of the path on 5 vertices has eigenvalues 0, plus or minus 1, and plus or minus root 3. And so you can run the same argument and prove that there's no PST between the n vertices, the vertices degree 1 in the path on 5 vertices. Now, when you get to 6, you find yourself having to write down roots of cubic. And I've never had to write down the roots. I mean, there is a formula for the roots of the cubic, but I've never had to use it in my career. And I don't intend to start now. So you need different argument to deal with longer paths. In fact, the only paths that admit perfect state transfer are the paths of length 2 and length 3. And we will eventually prove that. Okay. So yeah. So uh, so and so we have a proof there's not no PST on paths length 4, length 5. Basically, this obvious stuff we're doing at paths was first worked out by a paper by Chris Dundle and others, and they wrote down a proof that they claimed there was no PST on a path. What they actually sketched a proof of is there's no PST between the vertices degree 1 on a path. The general problem is a bit harder, but we'll come back to that later on. I talked about the eigenvalue support, and I said it's a collection of ordered pairs, and it seems a little bit funny to think of them as eigenvalues. The reason we do that is because when you're doing it with pure states, you can simplify the definition of eigenvalue support. So I'll do that now. So if you got your density as a pure state, okay, so then I can assume as ZZ starred, where Z is a complex vector of norm 1. And as I remarked earlier, then ER ZZ starred ES is non-zero if and only if both ER EZ and ES EZ are not zero. And so the eigenvalue support of D, well, it's written out according to definition. And so in fact, it's determined by the set of eigenvalues theta R such that ER times Z is not zero. So if you're dealing with pure states, you can simplify the definition of eigenvalue support. Okay, you just say that it's given by this condition. Okay, and so we'll be using that from time to time. On the other hand, if you're not dealing with pure states, then you've got to go back and play with these guys. Now, it's possible to prove that if I don't know what this, the diagonal terms. So if this is zero, now D is a density, so it's twice semi-definite, so we can write it as ER D to 1/2, D to 1/2, yeah, is equal to 0. And that implies that ER D to 1/2 is equal to 0. And that implies that ER D ES is equal to 0 for all S. So the diagonal terms matter. Okay, in the pure state case, it's the only terms that matter. In general, they still matter. So one way of thinking of it is you can define a graph as vertices of the eigenvalues, and you put an edge from R to S if ER D ES is not 0. That gives you a graph. Okay. Now, if there'll be a loop, there are loops on vertices. If there's no loop on a vertex, then everything in that row and column is 0. So you get a graph with one loop on each vertex, and that can be fun to play with. But the point is that the diagonal case, if the diagonal entry is 0, if that's 0, then ERD ES is 0 for all S. Yeah, and okay, I'll state the theorem. How am I doing for time? 14. So when I talk about pure states, or the eigenvalue support of a pure state, I'm basically going to mean this: the set of eigenvalues theta R such the projection of the vector Z is non-zero. And so to simplify things a little bit, and the eigenvalue support of the pure state is a set of eigenvalues of the restriction of A to the subspace generated by applying powers of A to Z. The first thing you've got to be a little careful. Technically, this is not a restriction. Normally means that you restrict the domain, but we're doing more than that. We're restricting the domain and the codomain because we're saying now we've got this subspace, and so A maps vectors in this subspace to vectors in that subspace. Okay, and so you've got an operation taking vectors in that subspace to itself, and so it's represented by a linear map. And this can get a bit confusing because you're starting with n by n matrix, and now you're representing it by another matrix. And this second matrix will have dimension equal to well, m by n, well, k by L by L, well, as dimension of this space. Okay, so I'm going to take that as given. The comment is if B is the matrix which represents the action on this subspace, the eigenvalues of B are simple, and the character polynomial of B divides the character polynomial of A. Now, we don't care too much about this condition. The point is each eigenvalue in the eigenvalue support is an eigenvalue of A. Okay, and secondly, and this is important, and so I need to prove that. And am I going for time? Yeah, okay, so this will do. So we're looking at this subspace. And now the first thing to notice is, although this is spanned by infinitely many vectors, it's also spanned by the projections of Z onto the eigenspaces. And so this is a finite dimensional subspace equal to this dimension equal to the size of the eigenvalue support. And the dimension of this is equal to the number of eigenvalues theta r such that the RZ is not equal to 0. Now, that takes care of the statement that the eigenvalue support is a subset of the eigenvalues of A. You need to be a bit careful about the simplicity, because the simplicity depends on to prove simplicity, I need to assume A is symmetric or emission, depending on the details. Okay, and so this claim is false if A is not emission. Okay, now I'll probably put some version of this on the assignment questions. Okay, so that the eigenvalues are simple. So that gives us we have a reasonable handle now on the eigenvalue support, and I will stop there for today. Yeah, that's about it. There's one eigenvalue that's always in the eigenvalue support, and we'll come to that next. Okay, so okay, any questions?